Okay, so you hopefully watched the other video about the alternating series test. Just want to go over a couple more examples and then introduce a new topic briefly, hopefully. So this series that you see here is an alternating series, and I like to go ahead and explicitly state that just as part of my evidence. It's an alternating series because of the -1 to the n plus 1 power. Well, let's think about, do the terms approach a limit of 0? So as n goes to infinity, the limit as n approaches infinity of 2 over n squared plus 2 does indeed equal 0. And then the third condition that has to be met, is if I have a to the n plus 1, the absolute value of that term has to be less than the a sub n term. So let's go up here and input an n plus 1. Let's compare these. Now, is it true that the term on the left would be less than the term on the right? Yes, because at n are positive integers, and because n are positive integers, we've just made the denominator on the left bigger, and that's going to make the overall value smaller. So since those three conditions are met, then we can go up to the series and say, therefore, converges by the alternating series test. I like to explicitly state that it's alternating as part of my justification. That's why I wanted to go over this problem. Okay. The next problem, it looks like an alternating series, and it is, but the alternating series test is only a test for convergence. This guy, let's go ahead and write out the first couple of terms. So let's plug in a 1 first. So -1 to the second power makes it positive. And then we're going to plug in a 1 here, and we're going to get 2 over 1. So that's our first term. Let's plug in a 2. So 2 is going to equal, plugging in a 2, we're going to get a negative. Then we're going to have 3 halves. Let's plug in 3, 4 thirds, and so on. Okay, so the limit of the terms in this problem, the limit as n approaches infinity of the terms, it's going to oscillate. So this would be an oscillating series. So it would be positive and then negative and then positive and then negative. So it does not approach, the limit does not approach a finite value, but the limit of the terms does not equal 0 for sure. The terms are getting greater in magnitude, and so the limit of the terms does not equal 0. Therefore, this series diverges by the nth term test. So I just want to have a little, do an example with you to show that the alternating series test is only a test for convergence. If you have a series that alternates where the limit of the terms does not approach 0, you would use the nth term test to say that it diverges. Okay, so a related topic is called absolute and conditional convergence. If the series, the absolute value of the terms converges, then the series converges absolutely. So if a series is alternating and we remove the alternating aspect of it and it still converges, we say it converges absolutely. If it only converges because it's alternating, but you take the absolute value of the terms and it diverges, then we say it converges conditionally. So example A, So if I were to remove the alternating part of this series, I would get 1 over n. And hopefully you recognize that this is the harmonic series, and then it diverges. Let's talk about the series as written. The series as written is alternating. Let's go ahead and find the limit as n approaches infinity of 1 over n. So that limit would equal 0 because the denominator would be getting bigger and bigger as n approaches infinity. And let's compare 1 over n plus 1 and 1 over n. So the one on the left is indeed smaller, and that's our third condition. And since all three conditions apply, we can say that this series converges by the alternating series test. However, and actually this guy has a special name, he's the alternating harmonic. And you can just use that as a justification too. The alternating harmonic always converges. The harmonic diverges, but when he's alternating, he converges. So since this series that we're given converges when it's alternating, but otherwise diverges, we're going to say that that series converges conditionally. It is only a convergent series because it's alternating. We remove the alternating part, no longer convergent. Example B. Let's take a look at the non-alternating counterpart of this series. So if I take away the -1 to the n, the part of the series that makes it alternating, I have n equals 1 to infinity of 1 over n squared. Hopefully you recognize this as p series. So in this example, p is equal to 2. P is greater than 1. So therefore, this guy converges by p series. If he converges without being alternating, he's going to definitely converge when he's alternating. So this one, since it converges without even needing to be an alternating series, we're going to say that this series converges absolutely. Always going to converge whether it's alternating or not. Okay, next one, C, we see an alternating series. Let's take a look at this term. What does this term tell us about the convergence of the series? Well, the limit of that term as n goes to infinity is not 0. So I know the limit as n goes to infinity of this entire series is not going to equal 0. So since the limit does not equal 0, then we just say the series diverges by the nth term test. There's no way it's even going to converge even though it's an alternating series. So diverges by the nth term test. So there's three options really a series could have. It can diverge, it can converge conditionally, it can converge absolutely. Okay, last example. So this guy is alternating because of this cosine pi n. Because cosine of pi is equal to 1, or -1. Cosine 2 pi is equal to 1. Cosine 3 pi equals -1, and so on. So the cosine part of this makes this series alternating. Let's take a look at this. So let's examine the series limit or n equals 1 to infinity of 1 over root n. Well, hopefully again you recognize that this is p series and p is equal to 1/2. So since p is less than or equal to 1, therefore that series diverges by p series. Let's go up to examine the series as written. So the alternating series that were given in the problem. So this guy, let's see, there's 3 conditions that have to be met for the alternating series test. This series is alternating. Let's find the limit as n approaches infinity of 1 over root n. That does equal 0, because as n goes to infinity, the denominators can get bigger and bigger and bigger. And then lastly, let's compare 1 over the square root of n plus 1 to the expression 1 over root n. Because n is a positive integer, this expression on the left is indeed smaller than the one on the right. So this series converges by alternating series tests. So if it diverges when it's not alternating, but it converges when it's alternating, there we can say that the series converges conditionally. So this outcome, the conditional convergence, that's where you need to show the most work. On part C, when we showed that it was a divergent series, not much work is needed. And likewise on part B, if we show that it converges absolutely, all that you need to show is that the series converges without being alternating, and then you can make the conclusion that it converges absolutely.